Hello everyone, CS Wart here, and in front of me are the first vertical furnace arrays. But before getting into those, which will require their own separate video next week, I need to explain how the vertical item distribution works on the back end for it. This is the same design that's being used in the furnace array, and you can see that's a really neat and small compact profile. I'll load up a stack of blocks into this chest here, and we see that it starts running. Now I only have 7 droppers in this setup, so 64 divided by 7 is 9, plus 1, so we'll end up with 10 items at the bottom and 9 in all the others. You can see a line of copper bulbs being pulsed up and down here. That's actually the items being distributed in real time. Pretty neat if I do say so myself. And what we're doing is just having a signal loop through a line of observers here and then up this snaking pattern up on this side. We should be done about any second here, and we'll send one last signal through because we had one item through. One item left over. So we have 10, 9, 9, 9, 9, 9, and 9. Perfect. I'll go ahead and clear the system with a observer chain. Okay. So, how did I get to this point? Well, I did actually try this quite a few years ago, but because quasi-power exists, I couldn't get it to work with a T flip-flop design, which is what's needed to lock the hoppers. And I tried using sticky pistons and dispensers, but because quasi-power exists, it would always mess up and retract the piston or repulse the dispenser. Then when 121 came around, I have the copper bulb revolution, and I actually recreated a new design. This is a buffer of dispensers, and then we have a comparator read that for an observer to pulse the copper bulb, for this comparator to lock the hopper line. Now there is one flaw with this design, that is the dispenser will have the buffer will have an item as well as the hopper. Well, that's only true half the time, because when I pulse it once, we've now cleared the item from the hopper, but there's still one in the dispenser. So if I pulse it again, now we have to slowly wait for it to refill. And that was just a problem with this buffer-based design. There was too much delay, and so you'd end up with uneven cycles. Then I decided, wait, I should go back to that design. And sure enough, having a 1-block T flip-flop, which is not affected by quasi-power, and it doesn't power its neighbors when directly powered, it was the perfect solution. So, here's how this works. We load up items, a comparator sends a signal for this sticky piston to push the note block, and we start sending the signal down, this line of observers. On the first observer, this observer turns off this copper bulb for this comparator to unlock this hopper for it to push its item through, because the hopper below it is still locked. Then, 2 ticks later, this observer is able to be detected by this observer for this copper bulb to turn off for this comparator to deactivate this hopper, and you get the point. It goes all the way down to the bottom, and we end up with one item in each of these. Then, when we get to the bottom, we have a little bit of delay, again, just long enough so that we can have the items flow through and get to the very bottom here. Then we start a snaking pattern of observers back up to the top so that we can slowly, and that's the key word here, slowly refill the system. If we go too quickly, by having just a straight line, we end up with items in every other hopper. That's not what we want. We want them in every hopper to be consistent and very compact. So when we get to the top, we just have a small delay again of 4 observers to repulse the note block, and it repeats the cycle over and over again. Pretty simple. If you need a tutorial, I'll do that right now. So here is our output. You can make this anything you want. If you want chests for a storage system, or if you are going into a furnace array like I did, then this is where you'll be pointing your hoppers into. Okay, and I can even remove those blocks now. So we have all of those hoppers facing that way. Yep. And now I will go up diagonally 1 block from there, and this will be our input chest right here. A solid block there, and we'll go down every other block to the bottom, and 1 block out from that, I'll do a line of copper bulbs up to the top. We don't need to go up to the very top, only as high as the hopper line is. Then we'll fill in the checkerboard pattern here with more solid blocks, and put in comparators in each of those spaces. 1, 2, 3, 4, 5, 6. Okay, and when we get to the top, we'll go the opposite way with that one, going into a sticky piston with a note block, and 1 block out from that, we can start an observer chain going downward, as far down as the copper bulbs are, and then we can have a observer observe those observers to power the copper bulbs like so. Then the pattern I do on the bottom here for the timing, which you may need to adjust depending on if you're laggy on a server, is a note block, observer, solid block, note block, and then another observer. Then a observer facing down, 1 to the side, so that we're covering the note block to keep it silent, and then we start the snaking pattern. Down, side, side, down, side, side, down, side, side, down, side, side, down, side, and we don't need to go to the far end because we're already at the end of the copper bulb chain. So now we can have observers look at the middle observer in the chain here, going into the copper bulb, like so. And then when we get to the top, we again will go down one, or looking down, two back, and one to the side. And that's actually the entire system. But you do have to make sure that you have the copper bulbs on by default, so I'll just pulse it once, like that. And now I'll set up a storage chest here at the end, and put our input there. We'll do, 64 again. This will take some time, so I'll just do a quick tick sprint for a day. Okay. And if you notice, it was making sound. If you are annoyed by that, you can always place a block over top of here for when it extends out. So now we had 64 divided by 6. We should end up with 10 in 2 of them and 11 in the other 4. 11, 11, 11, and 11. Perfect. So that's the design completely. If you want to know if this works in Bedrock, the answer is surprisingly yes. Asterisks, you just have to make sure that the amount you put in is divisible by the number of distributions you have. So in this case 7, I need to have 63, otherwise it will break. The only 2 changes I did have to make was swapping out the note block for a trapdoor, because observers don't detect pulsed note blocks on Bedrock, and 1 less observer on the bottom. So instead of having 2 note blocks, or in this case trapdoors, I just used the power rail line going from the last observer into the one over here. And we'll see here that as soon as we get to the end here, we should end up with 9 items in each of the droppers again. Okay, nothing broke. We have 9, 9, 9, 9, 9, 9, and 9. Perfect. So, if you want to see how it breaks and how to fix it, if you put the wrong number in, whenever it gets to the very end, it will actually end up pulsing the one right above where you have your last item, and it will be in the wrong state. So we had 1 extra item, so one above it here. The copper bulb needs to be pulsed again. While it's not the most robust thing, it works on Bedrock, so hey, I'll take that as a win. Anyway, that's all I got for today. Thanks for watching. Goodbye.